All right. Well, I think I've got everything set up here. So basically at this point we're either essentially just have left to do is review. So I think I was thinking about it. One thing that would be good to review, because I'm sure you guys have forgotten at this point, was like the definition of derivative, right? In the tangent line, remember that? So let me just put it up here. Definition. If the limit below exists, then we define f prime of a as follows. So you guys remember f prime of a is the limit as h goes to 0 of f of a plus h minus f of a all divided by h, right? And alternatively, we can do f prime of a is equal to the limit as x goes to a of f of x minus f of a over x minus a. Now, which makes the calculation easier for a given problem? It's just, I never know. I just try one and see how it goes. And if I really don't like a particular approach, I'll go to the other one sometimes. Further, y equals to f of a plus f prime of a times x minus a is the equation of the tangent line at tangent line through a comma f of a, right? So let's work out a couple of examples from the definition, since it's been a little while, and the final exam is comprehensive, so let's make sure we have our bases covered there. I'll start with something real simple. How about f of x equal to 3x plus 2, right? And we want to calculate f prime of a from definition of derivative. All right, so here we go. Which formulation of the derivative do you want to use? The h goes to 0 or the x goes to a? Your choice. All right, we have a decider. Very good. All right, so f prime of a, and so I'm just going to write it out, limit as h goes to 0 of 3 times a plus h plus 2 minus 3 times a plus 2. Now, parentheses are not just your friends here, they're your lifeblood. I mean, without parentheses, you get it wrong. That parentheses important because that minus has to distribute to both of the terms in f of a here, right? And then we do algebra. So what's it look like? We got 3a plus 3h plus 2 minus 3a minus 2. You see some things canceling, right? You see it? Come on, get out of there. So the 3a and the minus 3a cancel, the 2 and the minus 2 cancel, and we're just left with this business here, right? So what happens? The h and the h cancel, right? So we just get limit as h goes to 0 of 3. Which is what? Three, right. So f prime of a here is 3. So this function is differentiable, right, everywhere. This makes sense for any a. And no matter what a we're at, the slope of the function is 3. This is not surprising, right? Because what are we looking at here? We're looking at a line with slope 3. So of course it has rate of change 3 everywhere, right? This is not surprising, this answer, right? Now, how have we been doing this derivative later in the course? What did we do? We introduced rules of differentiation, right? So we did like d dx of 3x plus 2, and what did we get? Pull the 3 out. It's been a while since we wrote those steps down, right? But we do linearity, pull the 3 out, break across the sum. Derivative of a constant 0, derivative of x with respect to x is just 1. So we get 3, right? So which is the right way of doing this differentiation? It depends on the instructions for the problem, right? If I say calculate the derivative using the definition of the derivative, I expect you to do it like this way, right? If I just say differentiate, well, don't do it this way. That's a silly way, right? We have a better way. So down here, right? See if I can. There's a lot of glare coming through this today. See if I. Maybe that looks better. Maybe. All right, let's do another example. I think looking back at this topic is helpful for you guys because it gives us a chance to review limits again, you know, but not just that for its own sake. So, I mean, I usually ask a question about this on the final because I want to review limits, right? But I also want to review the definition of derivative, and this gets me both without just asking a silly limit question, right? And time is limited on the final, right? You get 2 hours. I need to cover the whole course, so this is a good problem because it tests both your understanding of basic differentiation, the concept, how we define it, you know, as well as how to calculate limits. So it's typically, there's a problem like this in the final, yeah. Let's see here. So let's look at f of x equal to 1 over x squared. All right? And so let's calculate f prime of a. Now this one, I think that the x approaches a formulation is going to be easier. Let's see if it goes that way. So we're going to try the limit as x goes to a, and I'll write it out symbolic. Well, so we're supposed to do what? F of x minus f of a over x minus a, right? Okay, so for this function, we've got 1 over x squared minus 1 over a squared divided by x minus a. So I'm going to rewrite that a little bit different. I'm going to write that as 1 over x minus a times the fraction 1 over x squared minus 1 over a squared, right? Those are the same. So I'm just kind of reformulating this compound fraction as multiplication by a reciprocal because it's easier to think about that way. Are you guys with me? So, okay, so I want to make common denominator here, so I just basically cross multiply. I've got a squared minus x squared over x squared a squared. So can you factor anything here? The way these work, you will always be able to factor out like an x minus a for the problems that we actually calculate this way. I can't just say always, always, because things like sine or cosine or exponential require other sneakier tricks. But for like a rational function or an algebraic function, this kind of algebra tends to pop out. So certainly for polynomials. Okay, so this factors, right? That's a minus x times a plus x, right? So what's the reduction here? Like, you can cancel x minus a with a minus x, right? Let me make a little sneaky thing here. I'm going to pull a minus out of the x minus a minus x. So watch me, guys, because you guys see me do it. I'm going to put this minus right here. When I do that, I need to change this to x minus a. Agree? Or if you like, you could pull a minus out of the step above and factor x squared minus a squared instead. Whatever. Anyway, however you see it, this and that cancel. And we're just left with limit x goes to a of minus parentheses x plus a divided by x squared a squared. So can we take this limit? See, there's no division by 0 anymore, is there? Because we canceled that x minus a factor, so that removed the indeterminacy of the limit. And now we can just plug x equals to a into this. So what do we get? Minus 2a over what? A squared times a squared, right? Which gives us what? Minus 2 over a cubed. What is our assumption about a throughout this whole problem? Better be a not equal to 0, right? Otherwise, this calculation is, well, you can't really calculate the derivative at 0 for a function that doesn't even have 0 in the domain, right? We can only ask what the derivative is of a function for a point, at a point which is a point in the domain of the function. That's a fundamental assumption here. Now, what would this calculation have looked like in the other way of doing things, with rules and everything? So this would have just been what? D dx 1 over x squared, which is what? X to the minus 2, right? Which power rule gives me minus 2 x to the minus 3, which gives me minus 2 over x cubed, right? In other words, f prime of x is minus 2 over x cubed, right? Which then tells me that f prime of a is minus 2 over a cubed, right? Obviously, that is easier, right? But if I ask you to do it by the definition, then you have to try to do it by the definition, right? At least give it a try. You might get stuck on the algebra, but if you at least start the problem right, I will give you partial credit, all right? So what if we wanted to find the equation of the tangent line to y equals 1 over x squared at 2? How would that go? Well, we just go, okay, so we know what it is. It's y equals to f of 2 plus f prime of 2 times x minus 2, right? By definition, that's the equation of the tangent line. So I just have to evaluate the function and the derivative correspondingly at 2. What is f of 2? I'll do it in a different color out here somewhere. F of 2, 1 over 2 squared, that's 1/4, right? F prime of 2 is minus 2 over 2 cubed, which is what? It looks like minus 1/4, isn't it? Because the 2's cancel, and you just get minus 1 over 2 squared, which is minus 1/4. So here it is, 1/4 plus 1/4 times x minus 2. Y equals to that. There you go. That is the equation of the tangent line to this function at 2. Is this function increasing near 2? And what error did I just make? I put a minus quarter, and then I somehow changed it to a plus down here. So it's supposed to be minus.
Yeah, but how did you get that above it?
How did I get what?
Above that.
This?
Yeah.
That's the definition of the tangent line. That is a line with slope f prime of a, which goes through the point a comma f of a. If you plug in x equals to a into this formula, what happens? You get a minus a, which is 0. You get y equals to f of a, right? So this is a line that goes through the point a comma f of a and has slope f prime of a. That's the tangent line. So it's important to have this on your formula sheet, right? Because you guys are allowed a formula sheet page of notes for the final, right? Did I say that?
Allowed to take. Allowed to take it in.
I'm sorry?
Allowed to take it with us.
Yeah, you can take a page of notes to the final, sir. Did I say otherwise before?
We can take an index card into the test.
Yeah, I'll allow you a page of notes front and back for the final. So you can just, or if you'd like, you can bring your 3 index cards from before if that's easier for you. But if you'd like to write everything out on a page front and back, that's fine. I like college algebra. I have 3 pages. It doesn't matter. It really doesn't matter. I could give them a book. I could say, bring your algebra book to the final. It wouldn't make a difference. Either you can do those things or you can't. You can't look it up in a book in a time test. Anyway, so my point to you is you need to have this ready to use if the question's asked, Or you have to have a firm conceptual understanding. I'm looking for a line which has slope f prime of a and goes through a particular point. You can also take that approach, but my boxed formula is much easier. It doesn't require thinking through y equals mx plus b or anything like that. There it is, done, formula. We don't need to complicate it. Okay, so another example. Let's see here, f of x equal to the square root of 2x plus 3. So let's calculate f prime. Let's make a specific number this time. Find f prime of, let's say, 7 via definition of derivative. All right, so here we go. F prime of 7 Let's see, is that a good choice? 7. 14 plus 3 is 17. I'm trying to think if I can think of a good choice, guys. Give me a second here. That's fine. There's nothing terribly pretty with this particular formula. 7 is as good as anything else. Okay, so what do you guys want to do? H goes to 0 or x goes to 7? Let's do the x goes to 7. So limit as x goes to 7 of f of x minus f of 7 divided by x minus 7. All right, so limit as x goes to 7 of the square root of 2x plus 3 minus the square root of, when you plug in 7 into that, you get 2 times 7, which is 14. 14 plus 3 is 17. So f of 7 is the square root of 17. All right, so you've seen this kind of pattern before. Now this is an indeterminate limit, right? Because when you plug in 7 into the numerator, you get 0, because you get 17 minus 17, root 17 minus root 17, which is 0. And in the denominator, of course, when you plug in 7, you get 0, right? And this is always the case, right? All the derivatives that we calculate, they're always of this 0 over 0 type. This is the nature of the whole question. That indeterminate form is at the heart of calculus. But what can we do? So, for lack of imagination, what I'm going to do is multiply by the same kind of thing, but with the radical made into a plus. That sometimes will kind of like set something free, so to speak. So usually a good algebra trick here for this kind of thing is just to multiply by the same thing, but with a plus. Now I have to multiply by 1, right? Otherwise I'd be changing the, I can only multiply an expression by 1, right? I can add 0 to it, but otherwise I'd be changing it. But I can do that. That's just 1, right? I can multiply by that. And what happens when I do? Hopefully something nice. Let's see. So the square root times the square root gives me, well, I'll tell you what, would it be okay if I kind of skip a step here? Yeah, I'm going to skip a step here in a sense. So this is going to give me 2x plus 3, and then the cross terms cancel. See, this times this and that times that are the same, but with the sign difference. So those go away, and then you get minus 17. So the square root of 2x plus 3 squared gives me 2x plus 3. The square root of 17 squared gives me 17. That's why I have those, right? How does that simplify? What do you got? Looks like we got a 2x minus 14, right? 2x minus 14, which is what? That is 2 times x minus 7. Ha-ha! I can see the light at the end of the tunnel here. And I don't think it's a train. Let's see here. X minus 7. So you see what happens is by multiplying by that yellow factor, we created, as it happens, an x minus 7 factor, which can then cancel the x minus 7 factor. In so doing, removing the indeterminacy from the limit, And then in the next step, I can just plug in 7. Right? I think I can just plug in 7 in the next step. So you're always free to try to plug in the limit point. And if it just doesn't work, then, so be it. But you go back and you try to do some algebra to remove the indeterminacy. But here, we can plug in 7. And when we do that, if you look at that, we've got root 17 plus root 17 in the denominator. That's twice root 17. So arithmetic here, 2 over 2 root 17. So the answer is just 1 over the square root of 17. What does this mean geometrically? What does this graph look like, by the way? If you were to write y equals f of x, what would that look like? Let's see here. So we need 2x plus 3 greater than or equal to 0 for the domain. 2x is greater than or equal to minus 3. X is greater than or equal to minus 3 halves. So this is the domain of f, yeah? And so what you're looking at here is it starts at like minus 1.5, right? And it goes to the square root of 3 at 0, so it's about here-ish. And it's just kind of one of these deals. This is the graph. And then what we found is the slope at 7, here-ish. This is the tangent line, right? So what's the equation of that tangent line? Y equals f of 7, which is what? Square root of 17. Slope is 1 over the square root of 17, x minus 7. So there you go. There's the equation of the tangent line to y equals the square root of 2x plus 3 at 7. Okay. So anytime we calculate a derivative, we can write down the equation of the tangent line if we want. I have not always asked for this, right? We've done hundreds of derivatives in here. I've done maybe 10 or 20 tangent lines at most. Probably not 20. Probably not more than 10. Because it takes more time, And I do want you to leave this course knowing confidently how to calculate the equation and slope of a tangent line. That is an important skill for you to acquire in this course, right? But what is even more important is being able to confidently use the rules of differentiation to differentiate functions, right? So what I'm emphasizing today is actually not the most important thing. It's just something you've forgotten, which is why I'm spending a little bit of time on it, right? Because if you don't use it, you lose it. And you guys have not used this after test 1, right? Pretty much. When I was first teaching calculus, or maybe it wasn't even calculus. It might have been like a calculus 2 problem session. I forget. But I badmouthed the definition of derivative. I said, no one ever uses the definition of the derivative. Like, who wants to do that? It's horrible, right? Who wants to calculate limits? Like, we just do formulas, You use rules of differentiation. It's way better. And then, like, I got a talking to by the professor. He's like, all of my research is the definition of the derivative, because he's a numerical analyst. So, like, consider this. There are people who work in industry or applied mathematics who don't have formulas for the function. Like, and theoretically, there's some function that describes a physical process, right? But you don't actually have a formula that describes the physical process. All you have is data. You have data. And so you can take data and you can basically discretize the limit idea and just find the slope of data, just basically formally doing this with data without a formula. It's very simple. You just look at the change in y over the change in x for the data. You have x and y. You look at the differences between y and the differences between x for adjacent data, and that gives you the slope of the data, Right? Yeah. And it's kind of an art, but like all of this continuous calculus that we learn in industry, there's a corresponding like discretized version of it, which sometimes is more interesting to like applications. But I think to understand the discretized version, you should first understand the continuous version, which is easier. But you can always sort of take this continuous calculus and sort of granulate it for applications. It's one of the things I saw working for the government for a year that I did in the Navy. I never got any kind of suit or anything though. I was a civilian. I never actually said, like if you stay long enough, you can go and take tours on the battleships and stuff. And some people are really into that. I was like, no, I don't want to helicopter onto a ship that is small enough that you can feel the waves of the open ocean. No. No. Yeah, I was a civilian, so I work with contractors, but yeah. Let's see here. So anyway, I think these three examples give you a pretty good sense of what you're up against, these kind of things, right? So
this is from test 1, right?
test 1, yeah. That is true. Now, there's another kind of find the tangent line equation problem, which you probably haven't thought about in a while, too. Let's review that one as well. Implicit differentiation. You guys remember implicit differentiation? It's been a little while. What's the idea of implicit differentiation? It's somewhat connected to the related rates discussion, right? So I'll do implicit differentiation. I'll say find equation of the tangent line to x squared y squared equals x plus y at hopefully this won't go wrong. I don't know. I try to make these up, but it always blows up in my face. I'll make this x plus y plus 1. That'll fix it. Well, these always go badly for me. I'm going to try, though. We'll try it at 0 minus 1. Find the equation of the tangent line to this at 0 minus 1. So first of all, whenever you see a question like this on my test or final, you should ask yourself the question, is that point actually on the curve? Because if it's not, I can just write on my test, sorry, Dr. Cook, but this point is not even on the curve. Your question doesn't make sense. And then I have to give you full credit. You know? Or you could do the nicer thing, which is tell me about it, and then I can tell everyone, hey, sorry about that problem, you can skip it, and then you get bonus points. And the, admiration of your peers. So it's up to you. Selfishly hoard the information and save yourself time, or share. Yeah, that's what I'm saying. So if I plug in x equals to 0, y equals to minus 1, does it actually solve this equation? So I've got 0 squared times minus 1 squared. Is that equal to 0 minus 1 plus 1? I think it is. I got 0 equals to 0. So too bad for us. We actually have to work the problem. All right? So to find the equation of the tangent line, I need to find dy dx, right? My goal, find, let's say, dy dx at the point 0 minus 1, right? Okay? Once I find that, I know the slope of the line I'm looking for, and I can go back and use point slope formula to write down the equation of the line, right? So let's find that slope first. So what do we got? We got d dx of x squared y squared is d dx of x plus y plus 1. What do I have to do? I mean, I got a product, right? This is a product, so I have to use the product rule. So I've got 2x y squared plus x squared times 2y dy dx. That's the derivative of the left-hand side. On the right-hand side, derivative of x with respect to x is 1. Derivative of y with respect to x, well, that's just dy dx, right? We're stuck with that. So then we do what? We solve for dy dx, right? We solve for dy dx. dy dx times what? Times x, 2x squared y minus 1 is equal to 1 minus 2xy squared. So I put all the terms with dy dx on one side, and then I factored out dy dx, and I put all the terms without dy dx on the other side, right? Now that I've done that, I can solve for dy dx. What do I got? 1 minus 2xy squared divided by 2x squared y minus 1. Now, sometimes when I ask the question about implicit differentiation, I just ask the question, find dy dx using implicit differentiation, right? If the instructions to the problem were just that, we'd be done, right? But I asked a slightly more interesting question. I said, find the equation of the tangent line, right? So what do we have to do now? We have to plug in the point of interest into that formula to find the slope of the curve at that point. So we need to evaluate at x equals to, what was it, 0, y equals to minus 1. Notation for that is what I wrote before. So we got 1 minus 2 times 0 times minus 1 squared divided by 2 times, well, 0 squared times minus 1 minus 1. Whew. I always worry I'm going to end up with division by 0 or something here. It's my misfortune. What can happen is if I'm not careful, I pick a point which the derivative is infinity. Like that can happen if there's like a vertical, if there's a kink in the graph or something, the formulas can kind of get, there could be, it's possible to have examples where the point makes sense for the curve, but it doesn't make sense for the derivative. But fortunately, this is not such an example. And as you can see, what we got is 1 over minus 1. Right? So the slope is just minus 1. So what's we want equation of line through 0 minus 1 with slope minus 1 is y equals to minus 1 minus parentheses x minus 0, right? And just to clean it up a little bit, that's y is equal to minus 1 minus x. There you go. That's the equation of the tangent line we're looking for here. Which again, I would point out is pretty cool because I don't really know how to graph that curve without like using, you know, some kind of numerical software or some sort or another, Desmos, whatever. And yet, there is the equation of the tangent line. And this is a very, very good approximation to this curve near that point. If you want to understand how that nonlinear model works close to the point with x equal to 0, this will do justice to that curve. And that's part of the beauty of calculus. We replace something nonlinear with something linear.
Could we have used that formula that you just erased?
No, we could not, because the formula I was just erasing is for, well, I mean, yes and no. So the formula I just erased was for f prime of a, but what's f of x here? What's the function? See, you can't tell me. See this right here? It's not y equals f of x for what x, for what f, you know? Can you solve that for y?
Yeah.
I mean, maybe. I might be able to, but it's ugly. It's quadratic in y with coefficients that are x. So I could look at like quadratic formula and I could come up with some sort of horrible formula for y. Yeah, I could do that. But I can change the problem ever so slightly and make it impossibly. All I got to do is like change the square to a cube, and that's definitely outside our algebraic acumen possibility. So the point is, this is implicit differentiation. We don't have the formula for the function. So the thing I just erased over there with the f prime of a, I don't have that. So for an implicit derivative, for the implicit case, the way it works is you do like y is equal to, you know, let's say y naught plus dy dx at the point x naught, y naught times x minus x naught. This is the equation of tangent line to, you know, equation with dy dx and at x naught comma y naught. So in my example, x naught was 0 and y naught was -1. There's not, the point is you have to look at x and y for the equation. Like you can't just, yeah. Let me look one more example like this just to try to make sure we understand it. If I had something like, you know, x cubed plus y to the 4th plus y to the 5th equals to, oh, I don't know, x. And actually, let me get rid of the x cubed on the other side and make it easier for myself. All right. And so you say, let's find equation of tangent line at, oh, I don't know, 48, comma 2. 2 to the 4th is 16. 2 to the 5th is 32. 16 plus 32 is 48. So that point works. All right, like I put y equals to 2. That gives me 16 plus 32, which is 48. All right, what's dy dx? We get d dx of y to the 4th plus y to the 5th equals dx dx, right? So this gives me 4y cubed dy dx plus 5y to the 4th dy dx equal to 1. So I think, Fabian, was it just you here when we reviewed logarithmic differentiation?
Yeah, probably.
I think that was, you were.
Parameters.
Yeah, that's right, that's right. So if you haven't, you should watch those to review, all right? I'm just saying, if you haven't, it's okay, but if you're just confident about logarithmic differentiation, then fine, but it would be good to watch those if you haven't. When was that? That was, seems like forever ago now. So we solve for dy dx, what we got? One divided by 4y cubed plus 5y to the 4th. See, because I can factor out 4y cubed plus 5y to the 4th here times dy dx, and that's equal to 1. Then I divide it to the other side to solve for dy dx, yeah? So there we go. Now, I want to find the equation of the tangent line, right? So I want to find dy dx at the point 48, comma 2. So I do 1 over 4 times 2 cubed plus 5 times 2 to the 4th. And it's kind of funny. What does the 48 do? Like our formula for the derivative has no x dependence at all, right? This is completely removed from our experience in the first 3 examples today, where the derivative was just a function of x, right? Differentiate a function of x, you get a function of x. Differentiate an equation, there's no telling what you're going to get for your formula for dy dx. It doesn't just have an x. It can have an x dependence, it can have a y dependence, it can have both, it can have neither. But here it goes. There's no x in the formula. So my point is you don't do anything with 48, just nothing, right? Plug in.
Not equal to 48.
When I write this, I mean take the formula for dy dx and put x equal to 48 and put y equals to 2. But in this formula, there's no x, so just nothing happens with it, you know? And what is that? That's 8. 4 times 8 is 32. 5 times 16 is 80. 80 plus 32, 112, I guess, if I can do arithmetic. So that's the slope of the tangent line. What's the equation of the tangent line, though? So you guys tell me. I'll start us out here. I'm going to say y equals to blank plus, I'll put the 112 in for you, parentheses x minus blank. So fill in the blanks for me. Two goes in the first one, right? Because that's the y. 48 in the other one, right?
Why 2 then?
Because it goes back to, this is the tangent line angle y naught plus the slope times x minus x naught. So the value of y where you're finding the tangent line goes here, and the value of x where you're finding the tangent line goes there. To answer your question more fundamentally, that's the equation of a line with slope 1 over 112, which goes through the point 48, comma 2, right? If you plug in x equals 48 into this formula, that goes to 0, you're just left with 2, right? So you can check that indeed this formula goes through the point 48, comma 2, and it has slope 112. That's the right tangent line. Anyway, there you go. So let me give you guys your test back. Let's spend the rest of the time talking about test 3 because there are still issues there to talk about. And
When you say y naught and x naught, that's not y initial and x initial.
no, it's just a label. You could put whatever you wanted there. It could.
In this instance, it's just basically what's known before we figure it out.
Yeah, the given point that you're interested in. Of course, you could write it for an arbitrary point just the same, right? I mean, you could write y, here's the equation of the tangent line at an arbitrary point. Y equals to y naught plus 1 over 4 y naught cubed plus 5 y naught to the 4th power times x minus x naught. I mean, there you go. This is the equation to the tangent line through the point x naught comma y naught, which is on the curve. And there are places where that is useful. But I was trying to make the question a little bit less abstract, so I put a number in. That's all. Let me see if I can get the projector working. Have I ever got it working in here? I don't remember. So I would say you guys need to work on U substitution more. You're not quite where you need to be yet. I see some confusion between differentiation and integration. That is unfortunate, but I'm guessing that that you'll get that out of your system by the final. I think that's just it's something new and. Nope, I've got no 4 here. I used to have a 4 on my ID. I think I posted the solution to test 3 a while ago, right? But we haven't talked about it, obviously. Let's see if I can. Zoom in a bit here. I'll turn off these lights, that might help. So I'm pretty sure if I was to ask problem 1, part A again on the final, you guys would get it right? Yeah? I think you can do part A, right?
Sorry?
Part A? I think you can do part A if I was to ask it again, yeah?
The first question.
Yeah,
Probably.
probably.
What did I do wrong here?
Differentiated. See, but we have to anti-differentiate because it's, right. See, you know better than that. I know you know better than that. So,
Yeah.
and then one of you flipped that was you. It's impossible to anonymously discuss solutions of students when you have 2 students to take the test, right? Like,
You don't have to be ashamed in here.
that's right. There is no shame. There is only learning. That's true, right? Like, your grade is not me telling you I think you're a bad person. It's just me telling you, hey, there's some math you need to fix, right? It's just that. We're all learning. But 2x minus 1. So I decided to use my handy-dandy formula for the absolute value integral because I like it. But of course, you could also break this into 2 pieces to do the integral. But if we make a u equals 2x minus 1 substitution, we have to change the bounds. You guys are not changing bounds. So you need to change the bounds. Or you need to go off to the side, do the integral, and then come back to the x bounds. But what you can't do is go from having bounds to not having bounds, and then going back to having bounds again. It's like you either keep the bounds the whole time, or you start a separate calculation, and then go back to the one with the bounds. Anyway, so du is 2 dx. So, hey. That's not cool. Oh, maybe I took a point off somebody here who shouldn't have had a point taken off, because I think there's supposed to be division by 2 right here, right? Dx is du over 2, missing a half.
I have
Yeah, so you're right. That was a half. You got it.
Yeah, over 6.
Yes. But, oh, yes. So the question mark, that's just a dot, dot, dot. So dot meaning, yeah, but yes, I will credit both of you back. How many did you lose on that one? How many did you lose because of the half?
Just at
1 point. So I give you both back
6 points.
I will give you both back a point. Do remind me. Although, honestly, I think that you're going to replace this score with the final exam score. In my heart, I believe you're going to make a better score than you made on this one on the final. I'm very hopeful for this because it is needed. Anyway, as I derived in class the other day, the antiderivative of the absolute value function is 1/2 u times the absolute value like that. And if I kept the half from the u, I should have had a half there. Sorry about that.
So is that solution wrong?
Yeah, it's wrong. I need to fix it. I should have thought about it. Like, you both have the half. I should have been like, wait a minute, why am I the only one without the half? Duh. I blame children. A child must have distracted me while I was writing. No, that's not true. I did it here. I got no excuse, really. Follow man. You can always blame things on the follow man. So sine squared is 1/2 of 1 minus cosine of 2x. And then from that, we can integrate 1 to x, integrate the cosine to 1/2 sine 2x, because the 2, we pull out the half, and you get pi over 4. So some of you were close to that, but didn't quite get it. Others of you were further away from it. So here, got to remember to add the constant, otherwise the problem doesn't make sense, Problem 2, go on here. Problem 3. Let's remind you guys again. Acceleration, we differentiate, right? Derivative of the velocity is acceleration. So we just have to differentiate, and that gives you minus pi sine pi t. The pi is from the chain rule, right? That's why I got pi there. And on the other hand, to get to position from velocity, I integrate. When I integrate 1 plus cosine pi t, I get a t from the 1, and I get a 1 over pi sine pi t from the cosine pi t. You can make a u equals pi t substitution if you want to see it, but that is what it is. And then, of course, plus a constant. We fit the constant to get us the 3, which gets us the constant being 2, and there it is. So I think you guys were like, so I felt like the solutions were sort of in the neighborhood of correctness, but they were far from, I get half credit because they were kind of, there was a lot missing, but I could also see evidence of studying, so.
I just forgot to do the acceleration part.
Yes, that is true. That'll hurt you. Here again, the bounds are like not optional, they have to be written. So the 5 dx, anytime you have a constant integrated over a region, you can just take the length of the region times the constant. That gives you what it is. So the length of this region is 4. Minus 2 to 2 is 4. 4 times 5 is 20. That's what this is going to work out to. Of course, I did the integral, and it worked out to 20. This together is 10 plus 10, which is 20. But that's how I think about that. When I see it, I'm integrating 5 over a region of length 4. That just gives me a rectangle that's 4 long and 5 high, so it gives me 20 area. That's how I think about it. But just to prove it to you guys, here are the steps. And then the other piece, even functions, so I can double the integral from 0 to 2. And you guys had that idea, so that was good. That was good. But there was just some quirk of the calculation, so you missed it. But oh, look, it worked out to 42. So I think it's a fair statement that if you have an answer on my test work out to 42, it's